All right, so for today, it's our very last section before our test next week. Operations with radicals and complex numbers. Okay, so this is where we're going to add, subtract, and multiply with radicals, with an I. I is what complex numbers are. So we're going to kind of put all of that together today. So first, we'll start with adding and subtracting. So with adding and subtracting radicals, they have to be like terms. Okay, just like when you add and subtract, like with x's or y's, right, they have to be the same to put them together. Same with radicals. So like 3 radical 5 and 7 radical 5, like terms. The radical almost acts like a variable where we can put those together. But like 4 radical 3, negative 5 radical 2, the radicals are different. We cannot put those together. Okay, but the big thing is you always want to look to see if you can simplify. Remember that rule I've been talking about simplify first? Yeah, it still comes into play. Okay, so we want to simplify everything we can, and then we'll look and see if we can put them together or not. Okay? So, number 1, radical 3 minus 5 radical 3. So my radical 3's are already simplified. Are they like terms that I can put together? Yeah, so what's radical 3 minus 5 radical 3? Thank you. Is negative 4 radical 3, right? Because there's like a 1 sitting here. So negative 4 radical 3. Okay, every year I get someone who tells me negative 5 because they just like take the radical off. You wouldn't just take the x off, right? So same idea. Number 2, 4 radical 7 plus 2 radical 28. Can I simplify either of those radicals? Now when I ask about simplifying radical, what I'm asking is, if I do a factor tree, do I find 2 of something that I can pull out? Yes, I can. All right, so we can do, the 7 doesn't do anything, but the 28, right, that's 2 and 14, and 2 and 7. All right, so I get a pair of 2's. So if the pair of 2's comes out, and then I have the leftover 7, what do I do with that? What do I do with that 2 right there? Yeah, it's going to come down and multiply by that one, so it's actually 4 radical 7. All right, this I'm just going to drop down, 4 radical 7. So then 4 radical 7 plus 4 radical 7, 8 radical 7. Okay, so from the very start, that problem looked like they weren't like terms. I couldn't put them together, but once you simplified the 1, they did become like terms that we could put together. All right, what about number 3? 5 radical 32 minus 4 radical 18. Okay, right, the way they sit, they're not alike. But we can simplify. Factor tree on the 32. It's 2 and 16, 2 and 8, 2 and 4, 2 and 2. All right, so looking for pairs. Pair of 2's and a pair of 2's gives me 4, and 4 times the 5 that's already there is 20. Do I have any leftovers? Yeah, just 1, 2. So I get 20 radical 2. All right, the other side of this, 18. I can do factor tree. It's 2 and 9, and 3 and 3. Looking for pairs, I got a pair of 3's. If I pull the 3 out, that's going to multiply with the negative 4 to give me negative 12. And I have a leftover 2. Are they like terms now that I can put together? Yeah. 20 radical 2 minus 12 radical 2 would be 8 radical 2. But that radical 2 almost acts like a variable where that doesn't change. I'm just kind of putting them together. All right, number 4. Why don't you guys try number 4 on your own? All right, so if you go through and simplify, right, we did our factor trees. 2 and 12, 2 and 6, 2 and 3. So pair of 2's would come out, multiplies there to give me negative 8, and I have leftover 6. Factor tree here. So a pair of 2's comes out, multiplies to give me 14, and a leftover 2. Are those like terms? No. So can I actually put them together any more than I have right now? No, I can't, because you were done here. So a couple people put those together and turn that into a radical 12. That is incorrect. Do not turn that into a radical 12, a radical 8. Don't do anything with those. Okay, that's like an x and a y. They are different. We cannot put those together. Okay? And it's all right to get answers that don't simplify as far as you might want them to. All right. So that was adding, subtracting, right? When you add and subtract anything with any kind of numbers, you need them to be alike to put them together. What about when you multiply? Do they have to be like terms to multiply them? No. Think about all the things you do in math. If you would distribute, right, like if you had 4 times 3x minus 1, wouldn't you distribute that 4? But it's not like terms with the 3x. So what? Okay, multiplying and dividing, they don't have to be alike, right? So looking here to distribute, radical 10 times radical 6, radical 60, right? The radical's still there. I haven't actually taken the square root of anything. I think some students yesterday were struggling with that a little bit. They come out of that radical when you have 2 of something, right? The 2 of them come out as 1. That's the only time that radical goes away. Otherwise, it's still there, right? And then we have radical 10 times 3. 3 radical 10. Good. Outside numbers, inside numbers, they don't multiply, okay? All right, from here, after you distributed, am I done? Take a look. It's not done if you have like a radical that you can find pairs in. If I do a factor tree, could I probably find some pairs in one of those? Yeah, we should definitely check that. Right, so this is 2 and 30, 2 and 15, 3 and 5. So when you do a factor tree on the 60, there's some pairs there. I got a pair of 2s, and then I have a leftover 15. If I do radical 10, can I find any pairs in that one? Right, if you try, some people just can't visually think through that. That's just 2 times 5. Some people yesterday were like, yeah, I got pairs. I did 2 and a 5. And I'm like, got a pair of what? Like, they're not the same. So I have a pair of numbers. Like, I have 2 numbers, but that doesn't give me 2 of the same. So that's going to stay inside there. So that's just 3 radical 10. Are those like terms that I can add together? No. So I'm done. I simplify each radical as far as I can, and if they're not the same, I'm done. I can't put it any further than that. Ooh, some of those get pretty, don't they? All right, radical 2 times radical 6 plus 5. So again, just distributing. Radical 2 times radical 6. Radical 12, good, because they're both inside numbers, so they can multiply. And then radical 2 times 5. It's 5, and then a radical 2. One's outside, one's inside. We cannot multiply them. All right, done or keep going? Keep going. Good. My first radical right there, if I do a factor tree, 2 and 6, 2 and 3, there's a pair of 2s, right? I have 2 2s. So that pair of 2s comes out, and I have a leftover 3. Other radical? No, I can't do anything with that one. So I have 5 radical 2. Like terms? Nope, so I'm done. I simplified my radicals as much as I could. If I have like terms, great, put them together. If not, then I'm done with it. Okay. What about 6? How do you multiply something like that? There's probably a 4-letter F word that most of you probably learned how to multiply something like that. Do you guys know what word I'm referring to? I see one head shake of yes. What? Say it again? FOIL. I'll tell you right now, I hate that word. That is like a 4-letter F word in this classroom. Okay? So you will learn that about me. I do not like you to use the word FOIL. I hate that math teachers teach that. Reason being, let me just kind of go off my little tirade just a little bit. It works like if I have, right, x plus 2 times x minus 3. It works, right? You have the first, the outside, the inside, and the last. It works. But what if I asked you to multiply like x plus 2 times x squared minus 3x plus 4? Does the word FOIL help you now? Nope, sure doesn't. I don't just have a first, outside, inside, last, which is why I hate that people teach that. The way I teach it, is you're just distributing, right? If I had x plus 2 times x plus 3, I will distribute the x to both parts. And then I will distribute the 2. If I have an extra term in here, right, something like that, okay, I distribute the x. Distributes everything. I could have a million terms. I just distribute it to everything. Then in the next one, I'll distribute that to everything. Okay, so to me, when I ask you, what do I do with this? Your response better not be FOIL. I'm probably going to tell you to watch your mouth. Okay, that's like a bad word in here. All right, I want to hear you say distribute, because that's what we're doing. We're just taking each term and distributing it to everything over there. Because it works, because a lot of times we have huge equations the further we go in this class. We're not just going to FOIL. Okay, we're going to distribute everything. All right, so working on number 6, first we will distribute the radical 5. So radical 5 times radical 15. Good, radical 75. All right, I haven't taken any pairs out, so that radical's still there. All right, then we distribute to the next one. So radical 5 distributes to negative radical 3. Negative radical 15. So watch your signs though, okay? Whatever sign's in front of it is attached to it. If it's a minus sign, that makes that a negative. If it's a plus sign, then it's a positive. Okay, then we distribute the other number. So 2 radical 3 times radical 15. Just 45? Just radical 45? There you go. 2 radical 40. I knew that's what you meant. Yeah, so outside numbers, again, would multiply. Inside numbers multiply. All right, and then distribute it to the other part. 2 radical 3 times a negative radical 3. So think about outside numbers give you negative 2. Inside numbers give you radical 9. Anybody's like warning lights going off right there when you see radical 9? You better be, because why? What's so special about 9? It's perfect, right? That's a perfect one. What's the square root of 9? That's 3. So what does this whole little term right here become? Yeah, because that's 3. So that becomes negative 6. All right. Any of my other radicals simplify? Maybe. What about the 75? 3 and 25, and then 5 and 5. So yeah, there's some pairs hiding in there. Okay. So a pair of 5s come out, and the leftover 3. How about the radical 15? No, that's just going to be 3 times 5. I don't find 2 of anything. So minus radical 15. How about that 45? I'm running out of space. Sorry, I'll do my 45 over here. I didn't leave space, sorry. 3 and 15. So are there pairs? Yep, we got a pair of 3s. So that's 3s come out. There's a 2 out there. It's going to make that 6. And then I had a leftover 5. So 5 radical 3 minus radical 15 plus 6 radical 5 minus 6. Any like terms I can put together? I don't know. So my answer is that ugly, long thing. It is. It's as simplified as it gets. Okay. So if nothing else, guys, this really teaches me, when I look at your work, if you understand what like terms are and how math really works. Because every year I have students who do that. They simplify it just like they're supposed to, and then they add 3 plus 15 plus 5 and put them together. And then they multiply like 5 and the 6 and the negative 6. I don't know what they're doing. Okay? They're not like terms. That's like having a 5x minus y plus 6w minus 6. Like, they're not the same. So they stay all separate. All right, why don't you guys try 7? Let me give you some time, because go real slow through your distributing, okay? But try number 7. All right, before we do this problem, One thing I've noticed from some of you, you don't recognize perfect squares. Okay? I blame that on your younger grades teacher that never made you memorize your multiplication facts. That's where I blame that. So if it helps you, make a list. What's 1 times 1? Did I just hear it too? 2 times 2? It's 4. 3 times 3? 4 times 4? 5 times 5? 6 times 6? 7 times 7? 8 times 8? 9 times 9? 10 times 10? 11 times 11? 12 times 12? 13 times 13? 14 times 14? 15 times 15? 16 times 16? So let's see how far you were going to go. I think it's, I was going to say, no, 296? I could be totally wrong on that. I don't remember. That's about as far as I can always remember, too. But seriously, the ones that show up the most is probably like 4, 9, 16, 25, 36. I think those are the ones we see the most. But like, look down at your paper right now. Did any of you leave an answer that's got one of those sitting under a radical? Walking around, numerous people stopped with a radical 4 sitting on their paper, or they sat with a radical 9 on certain problems. Like, guys, we need to see those and like red flags go off. Those are perfect squares. Don't leave them like that, okay? All right, so let's go ahead and look at number 7. So distributing here, radical 6 times 4 radical 3. Outside number is just going to give me a 4. Inside numbers gives me radical 18. All right, distributing to the next part. Outside numbers give me negative 3. Inside numbers gives me radical 36. Ding, 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 that's perfect, right? It's on my list. I'll deal with that in a minute. All right, distributing here. Outside numbers give me negative 8. Inside numbers give me radical 9. Ding, 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 that's another perfect one. It's on that list. All right, and the last one, outside numbers give me a positive 6. 2 negatives make that positive. Inside numbers give me 18. But again, every time you're distributing, you're looking at multiply outside numbers, multiply inside numbers. And they don't mix together though. All right, from here, I hope you start to recognize the perfects. Okay, square root of 36 is 6 times the negative 3 gives me negative 18. Square root of 9 times negative 8. Those are perfect. Take a look at these. You may not have recognized it from the start, but what do you notice about them? They're the same. Now, could you simplify both of them and then put them together? Absolutely. I'm lazy. I'm going to put them together first, then I'll simplify. So I have 4 plus 6, that gives me 10, radical 18. Okay, and again, if you separated them or simplified them first, totally fine. All right, from here, I can do a factor tree here. So 2 and 9, 3 and 3. So that's going to give me a pair of 3s, which will come out, which will turn that into 30, and a leftover 2. And then these are like terms. It's going to give me, what is that, negative 42? So 30 radical 2 minus 42. And we are done. So walking around, I saw that answer a lot. A lot of people are like, is that right? I'm like, I don't know. I didn't memorize the answers, but I saw it a lot. Okay. So anytime you guys are like, is this right? I'm going to be like, I don't know. I didn't memorize it. I was busy last night. I didn't memorize all the homework problems. All right. So questions here, are we seeing, I hope, maybe some of the common things we're messing up on. The other thing I've seen people do is like when they're adding, like if they were putting these together at this point, they would have turned that into a radical 36. They would have added those numbers as well. Stop and think when you're adding. If I have 4 candy bars and 6 candy bars, I have 10 candy bars. Did it change? It didn't change. They still say candy bars, right? I just have more of them. So when you're adding, like, think of it like that. I'm just kind of putting them in a pile. I remember when I was in school thinking about that, like, do I change the number? Do I not change the number? Kind of like with exponents. 3x plus 5x. Does it become 5x squared? Well, if I have 3 candy bars and I have 5 candy bars, do my candy bars turn square when I put them together? No, they don't. Okay, if they're bags of M&Ms, like they didn't change their shape. They're still bags of M&Ms. Okay, So just be careful when you're kind of putting your like stuff together. All right, number 8. So a couple people trying to look at that one, trying to figure out what to do with it. Any guess? What? That's what most people do, and it's wrong. She said distribute. Now, and I understand why people say that. I really do. Because the last thing that we were working on were exponents, and if there was an exponent outside, the first thing we did with it was we distributed it. Stop and think what we distributed it to when we did that. I might have had like 3x squared y to the 4th squared. I distributed it to every exponent. What is missing from inside that parenthesis? Oh, there's exponents. There's lots of them there, right? There's a 1. Yeah, no, you're fine. So like this one, take a look at what kind of thing I have on in here. Take a look at this problem I have. I want you to recognize the difference. What? There's no variables, but that's okay. That's not the thing I was looking for. What? That's okay. It's just a number, right? Square root of 11 is just a number. It's like 3 point something. Yeah. Say that one more time. Yeah, that's the difference. Do you see how these are being subtracted? Or they could be added, right? These are all being multiplied. This is one big term, right? Just one piece. If you have one thing inside of there, then yeah, you can distribute that. As soon as you throw a plus or a minus in the mix, you can't distribute that anymore. And let me show you why. What does it mean to square something? What's 5 squared? Why is that 25? Oh, it's multiplied by itself. If I would multiply this by itself, okay, that would be like 3x squared y to the 4th times 3x squared y to the 4th. Squaring means I multiply it by itself. Well, okay, I'd be like 3 times 3 is 9. What do you do with exponents? You would add them, so it'd become to the 4th. And then my y's, you would add them, be y to the 8th. Okay. So showing I multiplied them, is that any different than me distributing to here? It's no different. Okay, but what happens up here? To multiply this by itself, let's see, does that give me anything different than if I just distributed it? Okay, let's go ahead and multiply. What's radical 11 times radical 11? Which is, that's just 11. Radical 11 times negative 2. Outside, inside, right? So that's negative 2 radical 11. Inside. So distributing here gives me negative 2 radical 11. And then distribute to the last one. Negative 2 times negative 2 is positive 4. Okay, I got some like terms, right? I can do 11 plus 4 is 15. Negative 2 radical 11 minus 2 radical 11 is negative 4 radical 11. Can't do a factor tree on the radical. I am done. Had you just distributed the square, like we did here, would you have gotten this for an answer? Negative 11 squared would have just been 11, and negative 2 squared would have just been 4. I would not have ended up with this. Okay? So anytime you are squaring something, your brain should stop and think, what does it mean to square something? It means you multiply it by itself. So here, multiplying it by itself was the same thing as distributing the exponent. I get the same thing. That's why we do that, because we're lazy mathematicians, right? But up there, it's not the same. If you have a plus or a minus, you have to write 2 of them and actually multiply them out. If there's no plus or minus in there, then yeah, you can distribute. It's really fine. It's almost like, remember our lazy exponents? Where do they go to? Whatever it's right next to, right? It's too lazy to do anything else. Okay, so it's like on this problem, jumping across that minus sign, that's just too much work. I ain't gonna do it. Okay? So just think about lazy exponents. It's not gonna jump a plus sign or a minus sign, so I cannot do that. All right. So moving on to the next part here. Adding and subtracting complex numbers. All right. Is this much different than the radicals that I was just doing? No, because where do i's come from? They come from a radical, right? They come from a negative under a radical. Okay, so we just looked at radicals. Now we're looking at i's. Okay. If I add or subtract, do I need them to be like terms?
Yes.
Yes, right? Yes. I can't add a baseball and a hockey stick and say I have two of something, right? They're not the same. It doesn't make sense. Okay, so same thing here. When I'm adding, they have to be alike. So I can put my like terms together. Now, the hardest thing students have with this is they don't know what to do between the difference of a plus sign in between parentheses, a minus sign in between parentheses, or no sign in between parentheses. What if there's a plus sign? Do I need the parentheses? No, I don't need them. I mean, technically there's like a 1 right here. If I distribute a positive 1, does it change anything? No. So if there's a plus sign, I don't need parentheses. Okay? They're just irrelevant. They make no difference on the bearing of how I do this problem. Okay? So I can just put my like terms together. So what's negative 5 plus 6? Hard math today, right? And then I have a positive 8i minus 4i. That's just 4i. All right, like terms, when I add them together, that doesn't become I squared. Right? If I'm just adding them, putting them in a pile, it doesn't change anything. It's just more of them. And that's it. Okay, so I gets treated like a variable the same way those radicals, we kind of treat them as a variable, right? Like terms puts them together. Okay, so the next one down here, there's a plus sign. Do I care about parentheses if there's a plus sign in between? No, I don't care. It makes no bearing on my problem. So then I'm going to have 7 minus 3, which is 4. Then I have negative 2i plus I. Remember, that's like a 1 there. Yep, that unspoken 1. Negative 2 plus 1 is going to be negative 1i, or just negative I. Next one's got a minus in between it. Does that change anything? I hear a yes and I hear a no. It does. If I put a negative 1 here and distribute this negative sign, does it change my values? Yeah, it does. Here, if I distribute a positive 1, it didn't change anything, so I didn't have to. Here, it changes things, right? Negative 1 times 4 is that negative 4. Negative 1 times negative 9i is that positive 9i. It changes things. So if you have a minus in between, you need to distribute the negative 1. Now, on the one above that, if your brain is like, I can't keep track of which one's which, then always distribute. If I distribute a positive 1, it shouldn't change anything. You're not going to hurt your problem. I'm just lazy and don't want to. If you guys, if it makes you feel better, go right ahead. All right, otherwise, here, if a negative's in front of it, it isn't going to make a difference. All right, question always comes up, well, how do I know to go that way, and what about this one? Does this one get distributed too? Think about how you read. We read from left to right. Looking from left to right, there's nothing in front of this one. So this one's not going to change. All right, so I have negative 10 minus 4, negative 14, and then a negative 3i plus 9i. Good, positive 6i. But if you did not distribute that negative, you're not going to get the right answer. You have to distribute the negative throughout there. Okay, what about that one? Do I have to distribute something? Yeah, we absolutely have to. From left to right, the first part's not changing. Second part, though, that's going to change that to what? Okay, plus 2, and it changes that one to a negative 4i. All right, then we can put our like terms together. Negative 5 plus 2. And we have a negative 3i minus 4i. It's negative 7i. You want to know what probably most commonly happens on these problems? Can you guess what people do wrong all the time? No one knows? They distribute, yeah. They completely like forget the fact that that's sitting there, and then they like negative 5, let's distribute. 3i, let's distribute. No, we can't do that. Okay, there's a minus sign. When would you actually distribute? There was no sign. Good, because right, that absence of a sign, we always assume it's multiply. Like 4x. There's no sign in between them. We assume they're being multiplied. Right? But there's a sign. I'm not multiplying. Do I care about this plus sign? Does it affect my answer in any way, shape, or form? No. If you want to distribute the positive 1, go right ahead. It's not going to change anything. So negative 3i, I'm sorry, negative 3 plus 3. 0, let's cancel out. Then I have 9i plus 9i. 18i. Does it become I squared? No. Again, I have 9 of ice cubes, 9 more ice cubes. I have 18 ice cubes, right? They didn't change. They're still ice cubes. How are we feeling with all this? Good? You all right? All right, let me give you guys a couple minutes. I want you to do all 4 of these on your own. All right, first one. Do I have to distribute anything? Nope, it's just plus sign. So I have negative 7 plus 6. It's negative 1, and then a negative 3i minus 9i. Perfect. Okay, next one. Do I have to distribute anything? Yes. Change that to a plus 4, and that to a negative 2i. So then I have negative 5 plus 4. It's negative 1. Negative 8i minus 2i. It's negative 10i. Next one, do I have to distribute? No, it's just plus sign. So I have negative 2 plus 2. Cancels. 5i plus 5i gives me 10i. And distribute on the last one? Yep. Negative 5. That changes that to a plus 10i. So 3 minus 5, negative 2. Negative 4i plus 10i is 6i. Anybody get all 4 right? Good. Those of you that did not, are we okay? Or you're just not talking to me? You were probably the least talkative class I think I've ever had. It's good in some ways and not so fun in other ways. You guys gotta talk to me. I love that joke. Why are you turning in a blank sheet of paper? My answers are imaginary numbers. Is that what imaginary numbers means? No.